Morning for the first lecture topic is introduction. So before I start this program, I would like to know your background. Because I don't know whether you are a senior student or a basic student. So how many of you are master student? How many PhD students? What others are academics? So may I know your background. So in which research area you are working for the students and those who graduated, in which area, research area you have been working?
So, what I wanted to use.
Okay. That was the idea before. But optical. Okay.
My name is Rajkumar Tirmal. I am working in IRS assistant Noma.
Okay, fine. Because I just want to know your background. Then I have a so that I know that whether you know this area. Because I cannot assume that you know this area. Okay. So you all are familiar with first generation to sixth generation. So for the first generation, second generation, first generation, second generation digital. So now you take say you may not have used the first phone, maybe we have used it 3G or 4G because I myself got my first phone in the year 2000. So the Nokia phone. So then in that case, you may have used the first phone maybe 2010 or something. So now you see the first 20 years, so you have the mobile phones. So then second, third generation and fourth generation, you have the second wave mobile multimedia. So now if you take from 2020 onwards, so here everything intelligence network. So if you take the 2020 Internet of Intelligence things, so then now move on to intelligent Internet of Intelligence things. So here it takes everywhere. So the starting from computer science to communication. So many research works in artificial intelligence. So to take the computer science programs and computer science industry. So now high demand after this artificial intelligence. So to take any university, number of intake for undergraduates, or you say computer science, for example, in my department, undergraduate in takes 400 students. But if you take electronic engineering, less than 100 students. So that after this big data, artificial intelligence, so many students do their first degree in computer science. So here, if you take the artificial intelligence, machine learning, the computer science aspect is different, and communications aspect is different. So then, so you know the first generation. So you know the frequency and the main voice access only. So, so the disadvantages. So if you take the first generation, you may have seen the first generation phone. So poor battery life and no security. So the coverage is very low. So this is the first generation. So if you take the second wave, third generation and fourth generation. So here you have the key features, high data rate, then you have multimedia message support, then web browsing and 3D games. So here still in 3D, so we had the disadvantage. So here, so the bandwidth requirements for the high data rate and other one. So you take many countries, they dismantled the 3D networks nowadays. So in many countries, most of the countries, step by step, they dismantled the 3D network. So now mainly 4G and 5G. So you take the 4G, so you know the very familiar with, if you are not familiar with the long-term evolution. But so here, high data rate. So then, so since you have mobile banking, so the mobile app, so the enhanced security. So in some applications, you have the critical applications you have. So then they extended for voice over IP network. We have disadvantage. You take the hardware infrastructure. So the expenses, the spectrum, in many countries, very expensive. So the upgrade is time consuming. There are still disadvantages. So now 5G now is in the deployment stage in many countries. So the 5G is in now the deployment stage. So transition from 4G to 5G network. So today 5G, so here we can have very ultra fast data. So here the latency is much lower. So in millisecond. So here the very high security. So here numerous technologies, small cell network, pico cell, and femto cell. So different kinds of beamforming used in 5G. Then cloud infrastructure. So then the upgrade of the hardware, all many features are available in 5G. So you may have seen this triangle. You may have seen this triangle in 5G new radio. So 4G, so you call it like long-term evolution. So here 5G, we use the terminology new radio in So if you take the think about the first wave, you take the 3G, 4G. So you immediately in your mind comes increase the data rate. But when you take the 5G, so increase the data rate, that is one of the requirements. So here you have other two use cases. Massive IoT and critical IoT, these two in the 5G and beyond 5G. So in 4G, we have IoT in 4G. So if you take numerous applications all under this, so it has so massive connectivity, the ultra level low latency connectivity, or this is called critical IoT. So here, if you take the massive IoT, so the enhanced mobile, so the peak data rate, so 20 gigabits per second. So then 100 megabits per second and high mobility, the train. So if you take these other two pillars, massive type of communication and ultra level low communication. So you take massive type of communication, here the requirements are totally different. Here if you take the requirements, the 1 million devices per square kilometer. Say, if you take in those days, in every the home, so you have only one laptop or one desktop. Now you have so many IoT devices connected. Say, for example, if you take the CCTV camera, so whenever you go home, you go on holiday, you can see your CCTV using the CCTV through your mobile app. You can monitor your house. So front side, rear side, CCTV cameras. In addition, there are many other IoT devices. So nowadays, in some countries, the washing machine, so the electricity cost varies the off peak and peak time. So they can remotely control their washing machine using the smartphone. You can control your washing machine. So whenever the electricity is off peak. So if you take a household, you are going to have maybe 5 or 10 IoT devices. Maybe so if you take the in developed countries, in most of the countries nowadays, the electricity meter, gas meter, everything, smart meter. So earlier, maybe 20 years before, utility service provider will come and collect the electricity meter reading. Later it came, so you have to enter the meter reading online. Nowadays, nothing. So that means the smart meter, that is comes under massive IoT, smart meter. So the utility service it send the smart meter every day, photovoltaic every day. So then utility service provider they find the usage pattern. So in this area, people when they use the electricity, the usage high and then the usage low. So because frequently send the meter reading. So if you see the smart meter, you can see so at a particular instant, so how many, what is the usage of gas, what is the usage of electricity. So you can almost everywhere, 100% smart meter. So electricity, gas, smart meter. So if you take one area, millions of houses, so you are going to have millions of IoT devices, smart meters. Then you take smart parking. Say you take the certain cities, the car park is difficult. So you have in the car parking the smart sensors. So it automatically tells you where you can easily find a car park slot. Then you can straight away go there to the car park. So now if you did say the payment for the car parking, so using smartphone, say now you pay for 1 hour. Say if it takes more than 1 hour, you go to the bank, and if it takes more than 1 hour, then you can top up immediately using your smartphone. So car parking slots everywhere to have smart city. So that means here, so millions of devices are going to be connected through the cellular network. So here the requirement is different from here. Because if you take here, the data, you are going to transport packet of data. So here latency is not because you take smart meter reading now, so not really there. So you can send today night or tomorrow it can send. So this is not an issue. But here, the latency and Cuba, in some countries, they deploy the autonomous vehicle, driverless car. So if you take the driverless car, the latency is important, otherwise it will crash. So here is then in some cases you have remote surgery. So remote surgery means say in some African countries doctors because of their poor. So then the robot will do the surgery there, but doctor here he control the robot. So it's like when he cuts here, so then robot will cut the patient there. So the latency should be less than 1 millisecond, otherwise the patient will die. Then here you see autonomous vehicle, remote surgery, some applications, the latency issue. Here latency is not an issue. So therefore, this IoT and this IoT, they are completely different requirements. I'll come another slide later. Okay, so now we take the enhanced mobile broadband, so high capacity, so then broadband access, connectivity, so to be available everywhere, so high use of mobility, so bus, car, train, so and high mobility elements are totally different here. If you take the ultra low latency communication, so latency the efficient and bigger use here, as I said earlier. So intelligent transport system, remote delivery, latency less than 1 millisecond. So then high reliability also here, 99.8 reliability. So we'll see later what type of technologies to be utilized to achieve the reliability and to reduce the latency. So in 3GPP standard, so beyond 5G, they proposed some techniques to achieve this less than 1 millisecond latency and the reliability. So later, I can provide the numerical results how we can achieve less than 1 millisecond using some recommended schemes in 3GPP release 60. And as I said earlier, so here the requirements are different. So high density of the low data rate, latency is not it. But here the lifetime of the battery should be at least 10 years. Say if you take the smart sensor, you are going to have millions of sensors. You cannot replace the battery every year. So the requirement here is lifetime of the battery should be at least 10 years. So we can see the available technology for massive IoT later. So as I summarize here, so here this is the massive IoT, the critical IoT. The requirements are low cost, low energy. So because it should be low cost because we are going to have billions of devices. So if the sensor cost is high, cannot afford billions of devices. So then low energy. So lifetime of the battery should be 10 years. So energy consumption is very low. Volume of data. Here, as I mentioned earlier, so here the smart industry automation, the industrial control here, remote surgery. So then traffic, autonomous vehicles, so remote healthcare. It can latency to be the so now the massive IoT application, you have smart home, so then smart city as I mentioned earlier, so smart parking here have sensors, all sensors are connected. So then from you can find, you can get the access for all IoT sensors, millions of sensors here. Then smart healthcare. So if you take so first I take the massive IoT, then I come to the critical IoT. So if you take the massive IoT here, you can see non-IoT connections in almost flat. Internet of Things connected. So here the blue one. So every year exponentially increases. So here this year the devices connected to the internet. So here in 2025 it is going to be almost double. In another 3 years, the connected devices almost double. So now, I mentioned earlier, so the requirement here, so the requirement, so here we are going to have the massive IoT requirement is going to be TV only. So and it's already user or small volume of data. So it's going to be periodically transmitted to the base station. So here then some other applications. For example, the high mobility requirement in some cases you have delay constraints. So here we have numerous challenges we are going to have. So here in the numerous challenges, one of the challenges is going to be the burst in traffic. You will see later when you have massive IoT, burst in traffic means, say, if you take the normal traffic, smart meter to existing 3GPP release 13, 14, 15 standards for massive IoT can be used. But you take the burst in traffic means, say for example, if you take the burst in traffic where you are going to get is during a particular second, you are going to have in a particular area, the thousands of devices are going to try to establish a connection with the base station. For example, if you take pay as you drive, so nowadays almost all countries, the car insurance are monthly fixed. But in some countries, they introduce pay as you drive. So that is not fixed insurance, car insurance. So that means if you don't drive this month, you don't need to pay car insurance. But now current policy, every month you have to pay a fixed amount of car insurance. But pay as you drive means you have to pay only when you drive the car. Say if you park your, now you are on holiday, you park your car in your driveway or car park, you don't need to pay the insurance. But when you take your car to the road, the sensor in your car will establish the connection to the base station to the insurance service provider. Then insurance service provider gives the authority to drive the car. So that means your car is now insured because when you start, when you take the car to the road, the sensor will establish and get the approval from the insurance. So when you drive, say 5 hours, you drive a long journey. After 5 hours, you park the car. Then the sensor informed to the insurance service provider. So now no more insurance, no need to cover it because now you park the car. So you have to pay the insurance only for that 5 hours when you drive the car only. Say take for example big football match. Take a big football match. So 10,000 cars, 20,000 cars leave after the football match from the stadium. So these 10,000, 20,000 devices, cars are going to establish a connection with the base station. So that's the burst in traffic. During that 5 seconds or 10 seconds, so all these 10,000 cars will try to establish a connection with the base station. But to establish the connection, they have to select a preamble. Preamble means a sequence. They have to, so limited preambles are there. So 54 preambles are there. So all the devices select one of the 54 preambles and send to the base station to establish the connection. So then what will happen? Collision will occur. So this is the burst in traffic scenario. So for example, so we can mathematically model it and we found that only 20% or 30% will succeed when you have 10,000 devices under burst in traffic scenario. We will come back later. So how to model the burst in traffic, everything in the 3GPP release 16, they have the mathematical model. So in those kind of situation only, this machine learning would help. We'll see later, using this machine learning, dynamically changing the parameters every tenth of millisecond by changing the parameters dynamically. We can solve this, the burst in traffic problem we can solve it. So here there are numerous challenges in the massive IoT. So still it is so now when you take the massive IoT, we cannot use the normal human to human technology. Whatever we use in the human to human communication, we cannot use it for massive IoT connect. Because, as I mentioned earlier, lifetime of the battery is 10 years. So therefore, here we need low power wide area network. So the low power wide area network, so it's completely different from what is needed for human to human communication. So if you take the low power wide area network, here battery life will be 10 years. They'll cover 15, around 15 kilometers for the big station. So then the deployment cost will be very low because the sensor costs are very low. So the implementation cost will be very low. So if you say there are numerous technologies available for low power wide area network. If you take all these technologies, we can put into two groups. One is ISM band. Then, for example, if you take this and LoRa, these two, they use the ISM band. ISM band, so anyone can use. So for example, you can buy this LoRa or Sigfox for $2,000. You can connect hundreds of sensors, so you don't need to get the license from the authority. So here, these unlicensed band technology is useful for remote area. For example, if you take the farm, so you don't have the cellular coverage. Don't have the cellular coverage. Say you want to monitor the smart agriculture, or you want to monitor the animals in a big farm. So then you are going to have sensors and you are going to connect using the ISM band because you don't have cellular coverage. But in the cellular coverage, we have the narrowband IoT and are based on LTE standard, 3GPP standard. So that is used in the urban area because in the urban areas you have the cellular infrastructure, 10G infrastructure or 5G infrastructure you have. So using the existing LG infrastructure or 5G infrastructure, so you can use certain resource block for this IoT application. So if you take the cellular based the low power wide area network, it has numerous advantages. I will explain in the next slide. So only the LoRa and Sigfox useful only in the remote area, as I mentioned earlier. So in countryside, no cellular coverage, but you want to use it for farming or as agriculture. So in that case, you are going to use this LoRa. We are going to use this cellular based. Then this is the requirement of this low power wide area network. Take human to human communication. The requirement is this ground channel. So here we take the bandwidth. So human to human communication, significant band. But if you take massive IoT, the band is very small. You take narrow band IoT, it uses one resource block. So in LTE, you are familiar with the word resource block. One physical resource block means 180 kilohertz 1 millisecond. So here, in narrowband IoT, they use only one resource block. So for the smart meter reading, then they use only one resource block. So if you take high data rate application, they use 6 resource blocks. They use. So here the requirement band is requirement less. Here latency IoT, latency is not an issue. So here the range is greater than human communication. The range here up to 50 kilometers. So the low power wide area network is completely different from this human to human communication system. It's totally different. Say here you take this unlicensed band coverage and performance. Say if you take unlicensed spectrum for Wi-Fi or Bluetooth or Zigbee here, then unless the spectrum for low power wide area network for LoRa etc. The Wi-Fi Bluetooth here is is not one. In terms of coverage, so very low coverage here. To take the LoRa support, the box 2 coverage is greater than the Wi-Fi Bluetooth. So in terms of performance, Wi-Fi performance is better than Sigfox and LoRa. So if you take this box 1 and 2, they are the unless ISM band in terms of coverage. If you take the cellular based one, say here 5G new radio. So this is the performance versus coverage. If you take the narrow band IoT, this is by using the smart meter. You see the coverage. So here, the performance you don't need very high to send the smart meter reading or the park details. You don't need high performance. So that's what this cellular based low power wide area is used in the urban area. So this one for high data rate application. For high data rate application means CCTV. So this is low data rate is smart meter. Example. So if you take high data rate standard is it uses 6 kilohertz block, 16 to 180 kilohertz. This one just 180 kilohertz. So if you take from this time, so it is obvious that cellular based low power wide area network much better than the unlicensed plan LoRa and Sigfox. But so that's why here cellular based security network is utilized in North America. So some countries in Europe they use this LoRa Sigfox, but now almost all countries in the urban area they use the cellular based low power wide area network for massive connectivity. So here you can see the specific, the first two columns, low power wide area network in unlicensed band. So here, the licensed band. Say here, if you take narrow band IoT, say here, it uses one resource block. So here, the coverage 50 kilometers. For very low data. Take this one, so for high data rate. So here the data rate up to 1 megabit per second. But whether it is licensed or unlicensed, when you see this go, lifetime of the battery should be 10 years. The massive IoT devices lifetime with 10 years. So here you get module cost. So here the 5G is less than $2. So this is the summary of the LTE evolution IoT. So these are the LTE based this column LTE based low power wide area network. Okay, as I mentioned earlier, this low cellular based IoT has many advantages. But already infrastructure is there. Everywhere LTE infrastructure is there. So you don't need to install any new infrastructure. So here if you take 3GPP standard, even in 4G, there is this narrow band IoT. Only 4G there is. Then there is 14, 15, 16 onwards, they have info is narrow band IoT. So here these are the different features. So now we 70, 60 plus numbers. So they have more features. for narrowband IoT and EMPC for high data rate, narrowband IoT for low data rate application. So that's what. So here, narrowband IoT, it has so many advantages because it is cellular-based standard, 3GPP standard. So from no providing and it has lifetime. It gives a lifetime requirement, gives the range requirement, it meets the industry security requirement, all requirement. So in the second lecture, I will provide the technical details of narrowband IoT. Then how we can use the machine learning to improve the performance and the bursty traffic. I will come back to that later, the lecture 2 or 3. So today is the introduction I have. If you take the critical IoT, so this is other one, ultra level low latency communication. IoT. So different use cases you have. So automation, so here fusion. So here the different requirements you see the latency here in milliseconds. So from 25 milliseconds to here 1 millisecond, 35 different millisecond requirements you need. Take massive IoT, we don't need this return. This is not there in massive IoT. So these are recommended critical IoT. So in critical IoT, so ultra reliable low latency communication. Here everywhere the 99.99% reliability and the latency requirements are needed here. So here data rate, so depends on the application. For the traffic density, and connectivity, here you see, say here, 1 square kilometer only 1,000. Not like massive IoT. Massive IoT, you have millions. Here not millions. Here 1,000, 10,000, very low connection density. So now take the 16 use cases. So now 5G is in the deployment state. So 5G is development state, but there are numerous challenges still not resolved. You take enhanced mobile broadband in 5G. So there are numerous technologies of millimeter wave communication, high speed roaming, massive MIMO. There are numerous technologies to increase the data rate to big data rate to tens of gigabits per second. It's fine. But for the other two use cases, IoT and critical IoT, using 5G, numerous challenges have not been resolved yet. So here, if you take 6G, so 6G, the use case is similar to the 5G, 3 pillars, enhanced mobile broadband and massive IoT and critical IoT or other. Here, everything extreme work. So strengthen massive IoT, strengthen critical IoT, everything strengthened. In addition, in 6G, if you take the enhanced mobile broadband, so virtual reality, augmented reality. So here, the cloud environment is very, very unique, very, very high data rate. To take the massive IoT, as I mentioned, so in another 3 years, the number of devices to be the internet is going to be doubled from 16 billion to 30 billion. So here you have mission critical applications. So self-driving car, so autonomous vehicle, taxi, maybe in another few years, you will see in many cities, you will have self-driving car. So there, the latency and reliability is an issue. In addition, there's a new use case. This one, that is the combination of massive IoT and combination of the new use case in 6G. In 6G, for everything it has, is enhanced. So some other new scenarios. One is massive ultra-reliable low-latency communication. So that is the combination of massive connectivity and ultra-reliable low-latency. So now, how this is going to be achieved? So here, earlier you see, massive IoT requirement is totally different from this one. So massive is totally different. Now when you have it's when you have a combination of massive and ultra-reliable knowledge, how we are going to achieve this one we will see later. How this special use case could be achieved. So to achieve this, as I mentioned earlier in massive IoT for the velocity traffic, you need machine learning. So here also you need machine learning to achieve these two requirements. We'll see later. So as I mentioned earlier, you take 6G for everything extreme. So here extreme high data rate, extreme coverage, extreme low force, here extreme latency, extreme reliability, massive connectivity. So you have everything extreme. Say high data rate capacity, it can be achieved. So that is extended internet mobile broadband. There are numerous technologies, massive MIMO, teraflex communication, communication. Or this, you can move to the high the frequency from millimeter wave to terahertz. So then this one can be achieved. So here, if you take the IC technology improved significantly, so we can get the low for all these. Here, these requirements are very challenging. So here, less than 1 millisecond latency. So here, reliability everywhere 99.9999. In addition to this, need the new use case, extreme massive connectivity. So how we are going to achieve this one? So that is the right hand side tree. So left hand side tree related with the internet mobile. To take the right hand side, so we need less than 1 millisecond. This one, so massive connectivity 10 to the power 6 or 6, 10 to the power 6 per kilometer. So how we are going to achieve this? You see what type of technology is recommended in 3GPP, the latest release, the standard. So how we are going to achieve the latency we see here? We will see the detail later. How we are going to reduce the latency? To reduce the latency, one scheme is grant free. Say, take a conventional scheme, all are grant based. So the user equipment to establish a connection with the base station, they do taking process. So it takes long time. So that means here random access preamble, random access response, connection request, connection setup, scheduling, then only the data are handled. This is the conventional grant-based scheme that is currently used. But if we use this conventional grant-based access scheme, we may not be able to achieve less than 1 millisecond. Because this process itself takes long time, several milliseconds. So one option is grant-free. Grant-free means no handshaking. But if you don't have a handshaking process, that means as and when the packet arrives, immediately the user implements it to the base station. Then what will happen? Collision will occur. Because no handshaking means so two user equipment will select the same preamble and same collision will occur. So how we are going to solve that problem? So if the latency, definitely if you use the handshaking process, you won't be able to achieve less than 1. So another one, reliability. So here 3GPP standard release 16. To increase the reliability, they propose two schemes in the standard. In release 16, they use the repetition scheme to increase the reliability. Instead of transmitting one packet, the same packet is repeated certain number of times. Say you transmit one packet. Say instead of transmitting one same packet, if you repeat 5 times, at least one time it will succeed. So then reliability you can achieve 99.99%. But you are going to waste the resources because instead of one packet, same packet you repeat 5 times to improve the reliability. So in the standard 3GPP for both is repetition. So here two types of repetition. Propose this. The same packet repeat certain number of times, 5 times. So there is a decoding independent. So first packet repeated 5 times. So the decoding first packet, second packet, third, fifth packet, all are same packet repeated. So at the end of the fifth packet, the base station sends the acknowledgement to the user equipment. That is one. But you see, for example, the second repetition, if it is succeeded, then no need to repeat third, fourth, fifth because already second succeeded. So then they propose another one, proactive scheme. So the proactive scheme is if you repeat 5 times same packet, second one is succeeded, then no need to do the decoding third, fourth, fifth, no need. So acknowledgement will be sent at the end. So here the disadvantage is base station send the acknowledgement at the end of each packet. So overhead will increase. So there are advantages and disadvantages. So these are the two schemes they proposed in. These are the two schemes proposed in 3GPP release 16 to increase the reliability. By this way only you can get 99.999%. To reduce the latency, so they use the grant free. But if you have grant free, you are going to have collision. So then grant free is proposed, then repetition scheme is proposed. Then how about the massive connectivity? Massive connectivity means huge number. Say now you have millions of devices. So if you take one resource block, 180 kilohertz, say 1 millisecond. So you have millions of devices, so you don't have enough spectra. You use the conventional scheme, so frequency division multiple access, or like the current LTE, so OFDMA. So if you use the time division or frequency division duplexing, so then you have enough resources for 10 million, 1 million devices you don't have. So they recommend that implementation is very difficult. Remove the orthogonality. So remove the orthogonality. If you take in the time division multiplexes, particular time slot is allocated for one user. In the frequency division multiplexes, certain frequency is allocated. If you remove this allocation, so that means same resource block, same 180 kilohertz, same time. If more than one user, 5 users they use it, okay, then you can improve the because limited resources you can improve. So if you remove the orthogonality, you will have non-orthogonal multiplexer scheme. So now you see, if you take time division or frequency division, since resources are fixed, so then we cannot have basic connectivity. So if you remove the orthogonality, same resource blocks can be utilized by more than one user at the same time. Same 180 kilohertz, same time 1 millisecond, more than one. So they, after the initiative by some industries, so you can see for tens, thousands or tens of thousands of technical papers in removing the orthogonality in the power domain and the code domain. Some industries propose in code domain non-orthogonal multiplexers. Some industries propose in power domain non-orthogonal multiplexers. Remove the orthogonality because you don't have enough resources for 10 million devices. So then, here this is the power domain one. So in the power domain, how do they use same frequency, same 180 kilohertz? Users use power level. So in the 180 same frequency, one user uses power P1, other one uses power P2. So different power levels here. So here the base station. So this user is high power. This user low power. The base station allocate. They do the superimposed encoding. Then at the receiver, so this one high power, they can detect. So this user also detect the high power one first. Then this user low power one, try the high power one detect the system. Then decode the low power one. Explanation. Non-orthogonal multiplexer. So that means same frequency. Two users use different power levels. So the both users decode the high power user first. Here, then this one decoded is fine. This one after decoding this, then subtract from the total signal and then decode its own signal. So at the receiver, the user successively from the total signal, we subtract the high power signal and then detect. This is the simple explanation of non-orthogonal. But the problem is here implementation is very, very difficult. So hardware implementation, because you cannot cancel the interference perfect. Here you have to subtract. This one is very difficult. You have to estimate the challenge. Implementation wise, take removing the orthogonality in multiplexers. If you go to IEEE Explorer, you will get thousands of technical papers. But I don't know how many papers involved in the implementation. Hardware implementation is a complex issue. So until the hardware implementation program is solved, this one implementation by the. But this is the idea to support the massive connectivity. So now, so here, if you take the 6G new use case, if you take 6G new use case, you can see massive connectivity. So massive ultra available voltages. So massive connectivity, remove the orthogonality, low latency, free, then reliability, repetition speed. These three for the new use case in 6G, the combination of massive IoT and critical IoT, so the combination, we are going to have three technologies. Non-orthogonal multiplexer, glass with scheme, two types of repetition scheme. So this one and these are the ones proposed in the 3GPP release 16 standard. Yeah. So in these two proposed in the standard.
Which scheme is mostly
So, yeah, this proactive scheme because you don't need to wait till the last the repetition. But here disadvantage is after decoding every packet, so whether acknowledgement or not acknowledgement, we send to the user request extra overhead. So these two are recommended. Choice depends on the hardware, the developer. So these are both have advantage and disadvantage. This one you can overhead every. It don't have overhead. You know, At the end of the last repetition, only acceleration will be. Yeah. So you take 5. One of these one is succeeded. Then it will say the succeeded. But here, so after first one not succeeded in 4. Second not succeeded in 4. So extra over. So now we are going to see. So what are the now? So that means now the industries or academic research. So beyond 5G technology. So 5G technology, massive MIMO, millimeter wave, hybrid beamforming, the different types of coding scheme. So code of course and the LDPC coding scheme, numerous schemes in 5G. So to coordinate mobile broadband, with no wide area network, narrow band IoT, LTP. So central IoT application. But when you go for your 5G, so what are the current research topics? To take the current research topics, as some of you are doing your PhD in intelligent reflecting service or recall services here. So you take the material science. So material science people, they have, so here they have developed meta material. So here the recent advances in material field. So they wrote this new area of reflective elements. So here, so the intelligent reflective surface is there are many ongoing research proposals. So this intelligent reflective surface is going to be like wallpaper. So in a building, so these are going to be like a wallpaper. So to increase the capacity. So here we have reflection element. So here the reflection element amplitude phase is controlled by the FPGA controller. So this is one of the current research area in last year. So here reflecting signal here. So the reflecting surface here. So here we are going to have amplitude and each element. So this is going to be the receive signal. So numerous technical papers in this area. So here, not like massive MIMO. Here these elements are passive. So here noiseless, full duplex. So here no RFJ. Here you have RFJ. So there are many benefits, but still the implementation is the difficult issue here. So numerous advantages in the literature, the coverage is transmission rate enhancement. So this is useful for distance users. Here, whenever you have a block of stack here, this is a wallpaper. So this is any equipment or anything blocking server or anything. So from the wall reflecting server, you can reach the, say this, for example, is the Wi-Fi access point. From the Wi-Fi access point here, the user Wi-Fi, here they have blockage. So in the wall, we reflect and reach. So you can enhance the coverage. Then there are physical layers security and research work. So how to handle the US global signal and enhance the legitimate user. There are numerous research work integrated into the service in the physical layer security. Then the wireless power transfer. So actually, this wireless power transfer is around 5-6 years before it was a topic. But now it is not green communication, wireless power transfer communication. Because the efficiency is less than 10%. But but this reflecting surface can be utilized here also. Another Now, indication of understand. So there are numerous research going for in European countries to integrate the terrestrial network, the low orbit satellite, unmanned air vehicle. So unmanned air vehicle is so here to have UAVs, they are going to be the cellular network. So that is the self-connected unmanned air vehicle. It's another research topic. So here, the terrestrial network, so this no orbit. How we can integrate this is still one solution. The current trend is integration of this. So as I mentioned earlier, there are numerous work on this UAV trajectory, but most of the research only single UAV starting from 1 point, another point, 120 optimum trajectory to increase the capacity or data link with certain constraints. There are numerous papers, technical papers in cellular connected UAV. Then the machine learning, that is the purpose of this program. So machine learning for beyond 5G. So in enhanced mobile broadband, massive IoT, critical IoT, everywhere. So over the past 5 years or 7 years, numerous research activities in utilizing machine learning algorithms. So when you take machine learning algorithm, so mainly you may have the supervised learning, unsupervised learning, and reinforcement learning. If you take the supervised learning, falls under 2 categories: classification and replacement. So unsupervised learning, mainly clustering. So here we have the label data. So we have a set of input and output. So the mapping function is here you don't have the label data. So here mainly clustering based on certain criteria. So many literature work in the last 5 weeks in reinforcement learning for the different 5G use cases. So here in the reinforcement learning, you have one software agent. The software agent is like a software program. Software agent, an agent can be in the base station. So the agent is in the base station. Is dynamically optimize the parameter. You take a statistical, you take static optimization, conventional convex optimization. So the environment dynamically changing. So say if you take massive IoT cases, now the current time period may be the number of devices may be 100. Next time slot you will have 1,000. So within certain milliseconds, the parameters will change dynamically. So at the base station, many agents, multi-agents are there. So several industries are involved in this machine learning with say more than 15 parameters to optimize dynamically. Every transmission time interval GTI. So 50-60 parameters dynamically change. So multi-agents at the base station control the parameters. So we will see in the remaining lectures, I will explain the learning. So here we have agent. Agent observe the environment. So here environment is the channel conditions, number of user equipment, everything. Agent observe during the current transmission time interval, observe how many preambles, transmitted, how many preamps collided, how many preamps idle, how many user equipment successfully served, how many failed, all these during the previous time interval, they observe. Then at the beginning of next transmission time interval, dynamically changes the parameter using the software agents. So those kind of numerous verbs on this based on reinforcement. So here you have a software. Observe the environment and take the action. Means what parameters will be the best. Say for example, you see later in narrowband IoT, we have 9 parameters in narrowband IoT. So in 9 parameters, so agent will select, say for example, one of the parameters is repetition factor. So that means the preamp is going to be repeated 2, 4, 8, 16, 22. Of course, 128. Which one is best? So during this transient time interval, you observe next. At the beginning of next transient time interval, it changes from 2 to 16, 16 to 32, or 32 to 2. Dynamically changing by observing the environment. Whether traffic is heavy or low traffic burst and burst. So, agent environment, take the action, change the parameters dynamically. So you see that later. So this one also I will explain in the lecture about the learning algorithm. So how the two values are calculated. So when you have massive IoT, these two tables so become huge. So we cannot implement practically. So we will go for so then you have single agent, you have only one agent, solve the problem. So resource allocation problem. So observe the environment, take the action. So then there will be a reward. Reward means say we are going to give the reward agent. When they take an action, reward will be given if it achieves certain thing. If it does not achieve, that action does not achieve certain things, no reward, negative. So by that way, so we are going to define the policy. All these things, lectures I will explain. So when we have, practically we have more than one agent. So when you have more than one agent, so whether they are the cooperative agents or competitive agents. So cooperative agents and competitive agents is, so when you have 4 agents, for example, say for example, 10 user equipment. So user equipment have the software agent. So now, so these 10 user equipments, 10 agents, they can be competitive. So this user equipment is want to increase its data rate. It does not care about others. So that is competitive agents, multi-agent. Cooperative agents means, say, all these 10 agents, if everyone succeeds in certain data rate only, the reward will be given. So that is these 10 agents cooperatively achieve certain data rate. So we will see later in the following lectures. So how these cooperative, competitive reinforcement agents they work together. So here, so machine learning, deep reinforcement. So power control, network access, source allocation, and the routing also is the deep reinforcement learning scheme is used. So these are the three schemes. These slides I will more detail in the remaining lectures. Since in the introduction I just technical details, more explanation in the following lectures. I will provide for all these cases. Now currently, in machine learning is the current hot topic. So that means in 2016 or 17, Google proposed this federated learning. So last 5 years, this federated learning numerous applications. So federated learning means it is a distributed learning to preserve the data privacy and user experience. For example, your mobile phone, you have internet, mobile banking. So those are private. So those data cannot be given to the parameter server. So training purpose, you cannot provide certain data from your mobile. So therefore, your mobile phone, you have the local model, using your data you are going to train, and you are going to transmit the trained parameters only to the base station, the parameter station for global model training. You are not going to share your data in your mobile phone for privacy. That comes federated learning. So recently in machine learning, this federated learning is the current hot topic for this application. You may have seen in the one popular technical magazine. So one of the hot topics that make impact not only the telecommunication field but in economics and other fields is federated learning. So see, last year, this is one of the the topic we have a technical breakthrough in the different disciplines. So at the end of this program, I can explain the learning mode. So due to the time limit, so I skip many slides, but these slides will come during the remaining lectures. These slides will come. So you may have seen the and our body slides are there. So I will come back this later when I explain more technical detail. So considering your different background, so in the remaining the 400 slides, I try to avoid the mathematical derivation. That's the concept. We explain the concept. For mathematical more derivations and everything, you can prefer the relevant technical paper. But considering your background, I explain the concept as simple as possible, such that everyone could understand the basic. Then so whoever wants more technical detail, I can put the relevant references. You can find all technical derivation. Okay, so this is the end of my first lecture, lecture 1. So I have lecture 2 tomorrow. Then 3 and 4, 5, 6, 7, 8. Like the next 4 days. Okay, so can continue tomorrow. But you have the remaining of the 4 weeks one and on the start one.
We are going for decay repetition or proactive scheme.
Yeah.
But the overhead of the repetition.
Yeah, because so that's a trade-off. Because otherwise, if you don't have repetition, you won't be able to identify. So that is the trade-off. When you take available low latency, both requirements contradict. For to achieve you have to sacrifice latency. But they put both together because the critical application they need reliability also because you take autonomously remote surgery, need latency as well as reliability.
Because of grants,
Sorry? Grant for the year. Yeah. the resource block? That's the faculty of this block. That is the resource block components. Sorry? The resource block components. Yeah. Yeah. Remove it. Because we don't have the capacity, we don't have the capacity. So two users start at the same time for as position below. So that's why that should be separated. Yeah. So whether you for the handshake or this one, resource block is defined as and literature. So here to the data, you have to use some proper depends. For this one, so you take 5G, so you have new knowledge. Yeah. So not like this. So ये सब करिए space and time you
ये पैड होगा ओपन कैमरा यहाँ फोकस कर
yeah
मैं मंगवाया है मैंने
yeah
एक लैपटॉप यहाँ चाहिए
yeah
ऐप से कंट्रोल करते हैं यहाँ देख सकते हैं
yeah so this one yeah so this spring down so here is the most of the standards yeah standard
मेरे को एक मिला मैं लेके लगाऊं क्या है ये मैंने
यहाँ पे लॉक वगैरह किया यहाँ पे लॉक वगैरह
हाँ वैसे किस तरह भी पड़ेगा
आप चार्जर लॉक
Some slides I skipped, but I will come back. Those slides in the next.
तो सबको बात तो सबको ये गया है सुनील गया है कौन
So assemble here at 2:30.
कैसा रहा सर